Hello, this is module number 9, Mathematics in the Islamic World. And we have already talked about the significance of the contributions of the Islamic mathematicians and culture to mathematics in terms of the numeration system, that the Hindu Arabic numeration system was named partly for the Arabs, the Muslim merchants who went to India and borrowed the numeration system, brought it back to their lands and accustomed it or custom fitted it to what they needed and changed some of the numerals, changed some of the symbols, and then helped it spread throughout the Middle East, across Northern Africa, and into Europe. So we'll talk about that again in just a minute. And we're going to look at the PowerPoint with this one. And let me share the screen. There it is. Come on. Okay, here we go. So here's a map that shows you the extent of this empire from the 8th to the 13th centuries in the Common Era. And this is when it was at its greatest. You see in the far west, goes all the way across Northern Africa and into Europe, goes into Spain and Portugal. And it's very, if you get a chance to visit Spain and Portugal today, you still see the influence of the art and the architecture there throughout those countries. Then back as you move to the east, going across Northern Africa into the Arabian Peninsula, the Middle East, Iran, Iraq, all the way over bumps up until India. So there's the extent of that empire that we're talking about. And you can see, because of the land that we're talking about, how easy it was for them to trade with the Indian Empire or the Indian civilization. So they would leave from several different ports and then go over to India, trade with them, and that's when they would bring back that numeration system. Okay, this is an important slide. It's got several important messages on here. This first quote, "The ink of the scholar is more holy than the blood of martyrs," is attributed to Muhammad, the prophet, but also some people say, no, it's not. He didn't say that. That came from somebody else, or he said something slightly different. But I think the significance of it is that it illustrates the Islamic tradition of their profound respect for academics and scholarship. And that it goes back to the very beginning of the civilization, of the empire, that this knowledge, the development of knowledge, the building of knowledge, the acquiring of knowledge is really, really important. And education was important throughout this empire. And this empire became the unequal center of the intellectual world at this time in science, math, philosophy, medicine, education. All of these areas sounds a lot like what we said about the Greek Empire, doesn't it? And in fact, the Greeks had their library and academies in Alexandria and Athens, and the Islamic Empire had what became known as the House of Wisdom in Baghdad. And this was the center of learning for this empire. This is where both Muslim and non-Muslim scholars would come and work together, share their work, share what they were thinking about, work on problems together, and develop new material. And this was in Baghdad. It's known as the House of Wisdom, really important, just like that library in Alexandria was really important to the more ancient times. A really, really significant contribution was the translation movement. And part of this value of knowledge was their desire to bring all of the world's knowledge, all of the world's books, documents, anything that had been written throughout the world at that time, bring it back to Baghdad. They brought it back to Baghdad and they translated it into Arabic. Everything they could get their hands on, from ancient Greece, the Romans, India, anything they could get. If they got anything in China, they would bring it back. Egypt, what they could find there close to home from the Babylonians, brought it all back and translated it into Arabic. And that was really, really important, because without this movement, this translation movement, both translating it into Arabic and then writing it down on paper, without this, we would have a lot of this. We wouldn't have it today, because what we have today from a lot of what we have today from Archimedes, or probably everything we have from Archimedes, is not from the original Greek. We don't have what he wrote or what his followers wrote about him. What we have is a translation of that, what somebody else wrote about it, or what somebody else translated it. And then we've got the translation of a translation of a translation, and we've got it in Arabic. That's just amazing. This was huge to not just mathematics, but also science and literature, philosophy. All of this was important, but particularly mathematics. When you think about a lot of the ancient Greek materials from Archimedes and Euclid, Apollonius, Eratosthenes, a lot of that we have comes down to us through this movement. And again, a major innovation there as part of this movement was paper. They not only translated it into Arabic, but they were able to save it for us, write it down on paper. And so we still have those documents. We were able to keep those documents, save that material. Right. All of this was influenced by the ancient Greeks. They translated Ptolemy's work, Euclid. I mentioned Archimedes, Apollonius. Didn't mention Diophantus. We'll talk about him a little bit later, and many, many others. The Indian influence, we mentioned the Hindu-Arabic numeration system. They translated the works of Brahmagupta, Aryabhata, many of the other Indian mathematicians. Their everyday mathematics was a mathematics of practitioners. So this sounds familiar, sounds like what we said about the Indians and the Babylonians. They were surveyors, builders, artists, tax and treasury officials, merchants. All of these people used mathematics on a daily basis. And it was in these applications of mathematics that numeration system flourished. Not only were they able to represent numbers in an easy to understand, easy to represent way, but also then they were able to do the computation in ways that were much more easy to do than in other numeration systems. The greatest of the mathematicians during this period was a mathematician named Al-Khwarizmi. Al-Khwarizmi wrote 2 books, and both of these are important to put down on your list. The first one is, they're both long titles, Book on Addition and Subtraction After the Method of the Indians. Well, the Indians that he's talking about there are the people in India, the Indian civilization. And he's talking about that, what became known as the Hindu-Arabic numeration system. So Book on Addition and Subtraction, what he's saying there is, I'm going to teach you this system, and I'm going to teach you about the computation. So the book includes 9 characters for 1 through 9 and used a circle for 0. So it's easy to see how we got the symbol for 0 that we use today. He demonstrated how to write the numerals in the system, probably very much how you learned how to write them in kindergarten and 1st grade, and learned the difference between 34 and 43. How 34 means 3 10s and 4 1s, 43 means 4 10s and 3 1s. Even though it's the same 2 symbols that you're using, those 2 symbols represent very different numbers. He showed us how to do algorithms for computation, adding, subtracting, multiplying, and dividing, halving and doubling. Remember, we talked about that with the ancient Egyptians. Halving and doubling were really important algorithms for them, but they continue to be important mainly because that arithmetic was easy to do in your head. It was easy mental computation. The fractions that they used, this is kind of interesting. The fractions that they used were the same as the old unit fractions of ancient Egypt. So even though this is a civilization that was centered on top of the old Babylonian civilization that had the base 60 and had the sexagesimal fractions, they didn't use sexagesimal fractions. And even when they got decimal, the base 10 system, they didn't use the base 10 system for decimals and fractions initially. Came a little bit later. To start with, Al-Khwarizmi, 700-800s, we're talking about those old unit fractions. It was this book that introduced the Hindu-Arabic system to Europe. Now, this was written in Arabic. So you're going to see that very same statement in our next module, that another mathematician introduced the system to Europe. He introduced it via Latin. This was in Arabic, but he brought it over, or this work spread throughout this civilization, and you saw the map of the civilization, how the merchants were going across northern Africa up into Spain and Portugal, and naturally they traded throughout Europe. So that's how it got to that part of the world. And then I mentioned decimal fractions. In 1172, now this was several hundred years after Al-Khwarizmi, Al-Maghribi described the basic idea of decimal fractions. So he extended this process of dividing by 10 as you move from one place to the next, as you're moving to the left. As you move past the ones place, continue to divide by 10. So you get the tenths, the hundredths, the thousandths place. So that idea was described in 1172, but it wasn't until 1429 that another mathematician, Al-Kashi, demonstrated a full command of these fractions, of decimal fractions. And the notation that he used, instead of a decimal point like we use today, or the semicolon like we were using with the Babylonians, he used a vertical line. So he had the part that was greater than 1, and then a vertical line, and the part that was less than 1. Okay, the second book that Al-Khwarizmi wrote was an algebra book, the condensed book on the calculus of algebra and al-Muqabala. All right, now think about Al-Khwarizmi's name. Al-Khwarizmi's name gives us the word algorithm. So a lot of our words in mathematics come from, have an Arabic background, or they were born in Arabic. Algorithm is one of those. Algebra comes from the title of this book, Algebra. Algebra and al-Muqabala refer to solving equations and the strategies that you use to solve equations and move around the terms. So algebra says if you've got an equation that looks like A equals B minus C, you're subtracting on one side of that equation. He says you restore that. It's a reunion. You transpose the subtracted quantity to the other side. Now, that's not what we would say. Al-Khwarizmi would say you just move it. You move the C to the other side and you add. No, today we explain that in another way. We would say you take that equation A equals B minus C, and what you do to one side, you do to the other. There's a balance there. So you've got to keep that equation in balance by adding C to both sides. So on the left-hand side, you would get A plus C. On the right-hand side, you would get B minus C plus C, which simplifies to B. But Al-Khwarizmi didn't describe it as this balancing notion. He just said, oh, we're going to move it. And if you think about it, you know, that kind of might be the way you thought of it to start with. Oh, we're just moving it over there. You may not initially have thought of doing the same thing to both sides of the equation. Now, that's really important later on in algebra as you're working on more complicated equations, that to maintain that equilibrium, that balance state, you have to make sure what you do to one side, you do to the other side. That's not the way Al-Khwarizmi described it, though. And then in the case where you've got addition on one side and you need to subtract to simplify, he called that al-Muqabala, comparing or reducing, reunion, reduction. And the example there, A plus 2 equals 6, to solve that equation, we would say you subtract 2 from both sides. He would just say, move the 2 to the other side and subtract to get A equals 4. Okay. So we would describe those processes in a similar way by saying we're doing the same operations on both sides of the equation. Al-Khwarizmi called them reunion and reduction. Reunion is equivalent to what we call adding to both sides. Reduction is what we would call subtracting from both sides. Okay, but he saw those as two very separate processes, not doing the same thing from both sides. You're doing something very different with those two. Okay. Now, in this book, it's an algebra book, and it's a manual for solving equations and quadratic equations. Remember, the Babylonians solved quadratic equations as well. The Egyptians didn't. And even in India, we saw quadratic equations. But Al-Khwarizmi was very organized about this. He listed all the possible types of quadratic equations to solve. Now, don't forget, these coefficients had to be positive and the solutions had to be positive. So that limited the different types of equations that we have to solve. So you've got equations. Quadratic equations have three terms: a quadratic term, a linear term, and a constant term. We would say the general form for a quadratic equation is ax squared plus bx plus c equals 0. You've got a constant, that 0 on the other side of the equation, but you've got a quadratic term, a linear term, and a constant term. All right, so look at this. On these 6 types, all 6 of them have the quadratic term except for number 3. So number 3 leaves out the quadratic term. It's just the linear and the constant. But you can't have them both on one side of the equation. You can't have bx plus c equals 0, because the only way that could be true would be if x is a negative number. They didn't deal with negative numbers. So it has to be bx equals c. All right, 1 and 2, 1, 2, and 3, all 3 of those types of equations, you're leaving out one of the terms. In the first equation, you're leaving out the constant term. Second one, leaving out the linear term. Third one, you're leaving out the quadratic term. But again, everything's got to be positive. So you've got to have one term on one side of the equation, the other term on the other side. These are the only 3 possible ways that you can combine 2 out of 3 terms and keep everything positive. 4, 5, and 6, you've got all 3 terms. But again, remember, you've got to have something on one side of the equation. There's no way to solve ax squared plus bx plus c equals 0 if a, b, and c are positive. The only way that could equal 0 would be if x is negative. Well, they didn't consider that a possibility. So I've always got to have another number on, I've got to have numbers on both sides of the equations. So in 4, you've got the constant term all by itself. In 5, you've got the linear term all by itself. And in 6, you've got the quadratic term all by itself. So those are the 6 types of equations to solve. And in his book, he showed you a different solution method for each type. So if you were a student back at this time, and this was your textbook, you learned 6 different solution methods, and you applied a different one depending on the form of the equation you were trying to solve. Today, we see all quadratic equations can be represented in one standard way. And the quadratic formula can be used to solve all of them. We learn one formula to solve all of those equations. But Al-Khwarizmi said there is a different strategy to learn for each one of these solutions. And we're going to talk about one of those. Okay, this is where you've got the quadratic term and the linear term on one side and the constant term on the other side. The leading coefficient is 1. So if you had an equation that had something like 3x squared plus 6x equals 12, divide everything by 3, take care of that, and he showed you how to do that in the book, so that you could get the equation in this form where the leading coefficient is 1. And he said, have the number of roots, multiply by itself. Okay, add this to C. All right, we're going to go through this on a piece of paper. So let me stop sharing and come over here to the document camera. Come on, focus. There we go. All right, so the number of roots, the root is x. So the root is x. The number of roots is the coefficient of x. So halve the number of roots means take half of b. Multiply by itself. All right, well, 1/2 times b times 1/2 times b means just square that number. So when I multiply it by itself, I've got 1/2 b squared. And I'm going to write that as b squared over 4. Add this to c. So I add the constant to that quantity. So that gives me b squared over 4 plus my constant. Take the root means take the square root. So take the square root of b squared over 4 plus c. Subtract half the number of roots. So from this square root, the square root of b squared over 4 plus c, I'm going to subtract b over 2. That's the solution. That's what x is equal to. So when they would solve an equation, they would get one solution, right? One solution. Certainly never negative solutions, but even if it was an equation that might have 2 positive solutions, they only got one of them. All right, now let's take this equation and apply the quadratic formula to it. X squared plus bx equals c. We're going to use the quadratic formula. So the first thing I need to do is rewrite this equation in standard form. X squared plus bx minus c equals 0. And let me write the quadratic formula over here. If I'm solving an equation that looks like x squared plus bx plus c equals 0, the quadratic formula looks like the opposite of b plus or minus the square root, b squared minus 4ac all over 2a. Okay, well, in this case, a is 1. The coefficient of the linear term is b, but my constant this time in this equation is the opposite of c, not c. So when I make my substitutions into this equation, I'm going to substitute in the opposite of c everywhere there's a c. All right, so let's use this quadratic formula. X is equal to the opposite of the coefficient of x, which is the opposite of b, plus or minus the square root of the coefficient of x, which is b, square that, minus 4 times the coefficient of the squared term, which is 1, times the constant, which is the opposite of c, all over 2 times the coefficient of my squared term, which is 1. So that's x equals the opposite of b plus or minus the square root of b squared plus 4c all over 2. Well, let's compare that to what Al-Khwarizmi got. It's similar. I see a plus under the square root, a plus under the square root there. I see the opposite of b over 2. Let me see if I can get this to look like Al-Khwarizmi's form. All right, I'm going to unadd this fraction. I'm going to rewrite this as the opposite of b over 2 plus or minus, and you know, they only used 1, so I'm going to just use plus, the square root of b squared plus 4c over 2. All right, well, the minus b over 2 came after the square root, so let's rewrite it this way. Let's use the commutative property and move those two terms. The square root of b squared plus 4c over 2 minus b over 2. All right, let's compare it. That's closer, but this term for Al-Khwarizmi The fractions are inside the radical. So let's write this with the fractions inside the radical. Well, to move that inside, I need to write that as the square root of b squared plus 4c over the square root of 4 minus b over 2. Now I can bring that 4 inside the radical. So I've got the square root of b squared plus 4c all over 4 minus b over 2. And now let me write 4 as the denominator for each of the terms in the numerator. This is the same thing as the square root of b squared over 4 plus 4c over 4. I've got minus b over 2 on the outside. I'm close. If I write this b squared over 4 as b over 2 squared, simplify this fraction, I think I've got it. Oh, actually, I had it closer right there. I didn't have to do that. B squared over 4 plus C minus B over 2. It's the same thing. Basically, Al-Khwarizmi had the quadratic formula, but there were a couple of things going on here. One is, this is before the days of these symbols. He didn't even have a plus sign or an equal sign at this time. His algebra was what we call rhetorical. It was all described in words. So he had no way of saying, take the b and write it as b over 2. He had no way of representing the square root in this form. He couldn't write a formula with symbols. He had to describe it in words. And then secondly, remember, going back to those 6 examples, he had each one of those as different equations. So he had a different solution method for each one of those. Okay, let's go back and look at the next one. Okay, this is the one that we just did. And the next one is where you've got the quadratic term and the constant on one side, the linear term on the other. It looks very much the same, doesn't it? Have the number of roots, multiply by itself, subtract c, take the root. I think that was exactly what he had before. Oh no, instead of subtract c, he said add c. And then the last rule was the same. The last step was the same. The step that's different is that one that's right smack dab in the middle. Instead of adding c here, subtracting c on this one. Well, you could go through what we did on paper with this one, represent this and find out what the symbolic representation of this is and compare it to the quadratic formula. Okay. One last thing that he talks about in his book that we always study when we're talking about quadratic equations, and that's the discriminant, that number under the radical. Over here on the quadratic formula, the discriminant is b squared minus 4ac. And remember the rules that we learned? If that number is positive, you've got 2 solutions. If that number is negative, you've got if that number is positive, you've got 2 real solutions. If that number is negative, you've got 2 complex solutions. If that number is 0, you've only got 1 solution. All right, we'll read what Al-Khwarizmi said about it. If the product of half the number of roots with itself is less than the number connected with the square, then the instance is impossible. So that case he's talking about right there is when you get a negative number under that radical. And he's saying if you get a negative number under that square root, you're trying to take the square root of a negative number, that's impossible. He doesn't have words to say that. He can't talk about negative numbers yet. He's just comparing the 2 numbers and saying which one's bigger than the other one. But if the product is equal to the number itself, then the root of the square is equal to half of the number of roots alone. In other words, when they're equal, you just get that one solution, and it doesn't involve the square root at all. Now, he doesn't mention what happens when that product is greater than the number associated with the square. Right? So that's the case. And that's because for him, you'd still get one solution. Remember, he only took the adding the square root. He didn't take plus or minus. We have that special case because we've got plus or minus the square root. So for Al-Khwarizmi, you got one solution or you got 0 solutions. It's impossible. Okay. Now there's one more short video that goes with this lesson. And so be sure you watch it. It's about a geometric method for solving quadratic equations. See you soon.